Yeah, so maybe jumping into the third branch of machine learning, or a third branch. This is there are things that fall out of this taxonomy, but both supervised learning and unsupervised learning deal with, in some sense or the other, look at a fixed data set and learn something about it. There's another category called reinforcement learning, which basically involves training a machine learning model that's interacting with some kind of quote unquote environment. So this could be like a physics engine, this could be a power grid, this could be like a game engine for a multiplayer online game. But what your model is doing is it's trying to take some actions on that environment. So in the case of a game, what should the player do? The model might be trying to learn some kind of policy for how to take actions for that player. Or if you're trying to learn how a battery should charge or discharge on your power grid, then the action might be, how much should I charge or discharge? And what the machine learning model does is it tries an action. It gets feedback from the environment about how good that action was. So, in the case of the battery, how much money did I make? Did I destabilize the grid? And then based on that, it updates its underlying kind of parameters, that what's enabling it to generate its recommendation for what action you should take. And it just does that over and over again, tries to take some kind of action, gets some feedback, and does that over and over again. And so that's reinforcement learning. And in a lot of cases where we're talking about optimizing a heating or cooling system, or optimizing a power grid or something like that, something where you're actually trying to think about what are the actions that we should be taking in an automated way, you're often talking about reinforcement learning or something similar.
That's incredibly helpful when you look at the triangulation of just energy storage assets. For example, you've given the example, but also the state of charge of the battery itself, the operation of that battery in the most optimal manner so that you're not degrading it over the period of time that you care about financially. But how does it respond to the grid? What was your outcome financially? All that. I mean, it's just like an enormously complex set of information. And to have a reinforcement learning, what would you call it? Tool, agent? Mm-hmm. How do people characterize these in actual practice?
Yeah, so you'd call it a reinforcement learning agent, exactly.
Okay.
But tool also works depending on sort of whether it's the whole solution or a part of it.
Okay.
Yeah, and so I think these can be incredibly helpful. There are some caveats. One is that you often need either a real system you can test on or a simulated environment that is, realistic enough that you have some confidence that if your agent is learning to do something on your simulated system, that it actually tells you something about how the agent would behave on your real system.
And how long do you think that takes? Let's say it's a qualified team with real assets, and they're going to do a parallel practice. They'll have a practice system that's really not connected to anything that could hurt. And then you have a real system that you're just running, and some person is sitting there going, okay, on, off, on, doing it manually. What would be the timing? Is this like 2 weeks? Is it 15 years? When do you think people can get enough confidence with this reinforcement learning element agent to let it go?
Yeah, I mean, I think it can be a matter of years. And in some sense, it has to be in the sense that we do just really need to be dynamically optimizing power grids to be responsive to, higher renewables integration. But there's work to be done if we really want to realize that time scale. So these realistic simulators, for example, don't exist. And there are efforts to build, quote unquote, digital twins of the overall power grid, which is, really a real-time snapshot of what your power grid is doing. But I would say that's a solution for reinforcement learning algorithms that have already advanced along the readiness pipeline enough that you're in that last stage of testing. We don't even have kind of simpler simulation environments that are not pulling in all your real-time data, but where a power system operator, for example, has sat down and agreed, this is reflecting how my grid would actually work, what kinds of anomalies or intricacies I would actually see during actual practice. We need even that just basic simulation infrastructure along with agreed upon metrics so that if your method succeeds on the simulation infrastructure, you know what success means and you know what's next in order to test it out. And the other thing is reinforcement learning methods. They, have achieved really powerful performance in the last years. but they can fail and potentially catastrophically and in unexpected ways. And so bringing back this theme of, physics informed or domain informed learning, there's some work, including my own, that really tries to bring together concepts from robust control and control theory, where you can actually prove something about what your controller is doing with reinforcement learning, so that you're not just depending on like seeing in real life how your algorithm performs and kind of crossing your fingers that it won't break anything, or hoping, making your best guess, but really can you actually provably say something based on the mathematics of the system about what kinds of failures you know won't happen.